Greetings and welcome to Calculus in the PM. I'm your host, Mr. Shindelka. I'm recording this one, so I'm pretending that I'm... Okay, anyways, we've already looked at doing limits, and sometimes we can evaluate by imagining this tiny variable, or tiny amount h that's approaching 0, and you add it onto your x value. And then you plug it into your y value and you figure it out. We're really using the slope formula in this example. Anyways, and you imagine this amount h that's approaching 0 is the example we used. And you see what you get. And you can do this by chart. If you imagine that your h was 1, well, that's pretty small, but decimal 1's even smaller. Decimal 0, 1, and so on. 0, 0, 0, 1. Anyways, as you do a chart of values, it approaches, it seems to be honing in on one particular value. 64 in this case. That would be the value of the limit by doing it with a chart. It's terrible if you don't have a calculator to do those calculations. We've learned how, in some cases, you don't even have to re-enter it every time. You just replace with 0, 1, 0, 0, 1, etc. And your calculator just use the same entry over and over again. So it's not a ton of work with that kind of calculator. Then we said by picture with a graph. And I think we're approaching comfortable with the graphs, right? Well, we'll soon see. Because I gave you guys, I'm going to pause the video for a second here. I gave you guys some handouts here. And we'll just double check that we understand the graphs. And then we will look at method 3. And we're back. If you're just joining us, you have just joined Calculus in the PM. Okay, continuing on. Method 3, using strategies to evaluate limits that involve algebra. This is the most common method, especially when you're in university. Use direct substitution if possible, and I mentioned that I'm using examples from this Peason textbook here. Now, this is the easiest one. You can imagine a graph of y equals x, right? I'm going to just draw it and disappear in. Okay, here's the graph, I guess. I didn't need dotted. So if we had this, it's 1, 1, 2, 2, 3, 3, and so on. That's a continuous function, right? There's no breaks in it. So really, there's not much to this. If you approach 2 from the left on the x-axis and from the right on the x-axis, so 1.99, 2.01, etc. Doesn't it look like it's going to be 2? It's that simple. You can think of it as directly substituting the 2 into here, because there's no reason why you can't. Philosophically, it's not quite the same. I'll just say keep in mind that you aren't actually plugging in x equals 2. You are, but philosophically you aren't. You're imagining that as x approaches 2 from either side of the number line, the answer, this is the answer I get. I mean, I didn't say the answer. It is 2, right? Now, that means if I plugged in closer values, 1.999, 1.99999, etc., it's going to get closer and closer to 2. And from the other side, 2.0001. Does that make some sense? I don't know if the distinction makes any sense to you right now, but philosophically it's slightly different than just plugging it in. However, that's what it is. Now b, the function here, now remember, oh, I thought I was on the other tab. What's here is always the function, like here the function was x, right? The function is 19, so that is a graph, x, y, where you have 19 as a straight line. So from the left or from the right, as x approaches 3, the value is going to be 19. Okay, a constant, no problem. Now these first 4 are supposed to be that simple. So if you had this graph of x plus 3, the function is x plus 3. Keep forgetting that I changed pens. Anyways. So x plus 3 is my function. That's a straight line. So that means if I put in 4, I could think 6.9 and 7.1 and 7.01, 6.99. But what's it going to approach? The same as when you plug in 4, right? So as x approaches 4, This turns into 4 plus 3, right? And you don't even have to show your work there, I hope. We're going to just say it's going to give you 7. From the left or from the right, you would predict 7, and it is 7 by coincidence. Now this next one, -1. I did this. So I put -1 in here. You guys recognize that there's an asymptote here at +3, but this isn't at +3. That's the problem spot. So if I put -1 into top and bottom, I get, and I'll show the work here, 0 out of -4, right? So really, is that a valid answer? Pardon me? Yeah, it's 0. If you graph that, it's going to be crossing the axis when it hits -1. Okay? So, direct substitution if possible. First thing you always check. And you know what? Right now it seems, yeah, of course. Why wouldn't it? Later on, you're going to learn some techniques, and then you're going to forget some of them are easy enough that you can just directly substitute, and you're going to start factoring and stuff, and whatever. Now, the second thing you might go to, if after trying direct substitution, that's always the first thing, scan an equation, see if you can do that, or function, scan a function. If after trying direct substitution, you find a non-zero numerator and a 0 in the denominator, it's undefined, use this method. So non-zero meaning like 5 over 0, right? Then use this method. Because you know that it's undefined, but what we're going to want to see is, does the asymptote go up or down on both sides, really, is what we're checking. That's all we're checking. Is it's not just undefined, it could be going to infinity or positive or negative infinity. So let's think this one through. And if you can just visualize the graph, that's even easier. But we're only concerned about this. Well, let's just see here. Why can't we do this one? Well, on the top, we get 2 over 0. This is rubbish. You can't do that. That's undefined. Can we be more specific than undefined, right? So this is when you have a number over 0, you're going to do this. Now, I have n and d on the right of this little number line here. Meaning, my numerator, I'm going to just put, like I labeled it this time. I wouldn't normally label it. I think you can see this. X plus 4. And the only spot where we're not worried about the rest of the graph, we're only worried about around x equals -4. So really, we're only worried at 3.9, 3.99, etc., and 4.1, 4.01, that region. Don't worry about the other stuff at -6, etc. We're not worried. So back to this. So my number line, I'm not labeling a bunch of stuff. I'm not putting 0 on here. All I'm putting is -4. And then I'm thinking, if I have, I guess this is where my asymptote is, so I'm going to put, like you're thinking this is an asymptote, right? I hope you can identify it. Okay. For the numerator, x plus 6, what's that going to turn into? So if you put -4.1, just something slightly bigger, it's going to be positive or negative. That's all I worry about. Still going to be positive, right? The numerator is going to be positive. So I'm going to just put -4 plus 6, like -4.1 plus 6, it's still positive. And the denominator, -4.1 plus 4, that's going to be negative, right? You guys follow me? I'm not even worried about what the values are. If I'm using, oh, sorry, I'm talking, I said 4.1, and yeah, I'm going backwards on my own number line, aren't I? -3.9, let's just think about. My mistake. It's positive 3.9, -3.9, positive. Right? On this side. Anything you put in this neighborhood right beside -4, 3.99, etc. It's going to be double positive. It's going to come out to be positive overall, right? So it's going to be a positive side here. That means, what would the asymptote on the right-hand side look like? Going up or down? The positive numbers, so it's going to go sky high. That's really what we want to know, is that it's doing this.
Is that what we're trying to find?
On this side, yeah, because you can't come to a value. And then on the other side, the numerator is still going to be, when I do negative 4.1, sorry, before I was talking about that. It's still going to be positive on the numerator, but the denominator, negative 4.1, will give a negative sign. Overall, this side, and test it out if you don't know, like actually plug in 4.1, negative 4.1, if you're not into dreaming this up. Positive over negative, it's going to be negative. That means it's going to be dropping to negative infinity on the other side. So, I'm not graphing it really, I'm just showing that one section near negative 4, what's happening. Now, do the left and the right side have the same trend? Nope. And because this is a limit where we're looking at both sides, it didn't have the little negative sign behind the 4, meaning from the left only, or from the right only for that plus sign. We can't be more specific than undefined, or no answer. So we're going to just say the answer here to the limit problem is undefined. And we'll just take this away. This is why we couldn't do this, right? And just put this right beside, that's what you can do there. If they had both went up, you would have put and been more specific and put positive infinity. If they both went down, more specific than undefined is negative infinity. It's a better answer because it gives you which direction both sides are going. If they're one-sided limits, you'd be able to say positive or negative infinity. You guys got that down? Okay. I look at the people who are nodding yes, but I'm assuming the others do. In this case, I'm only going for 3 from the left. Let's just toss down on our number line here then. 3. We know that it's going to be an asymptote because x minus 3 all squared, so it's going to be 0 on the denominator. It's going to be 3 on the top, so it's going to be an asymptote. Can you guys, even without thinking of top or bottom, see if it's going up or down? Just think it through. I did the other one explicitly, but I mean, can you just visualize or think this through? If I put, from the left, 2.9 here, it's just going to be positive, isn't it? If I put 2.9 into this, sure, it might be negative, but you square it, and it becomes positive anyways. Incidentally, then it's going up, positive infinity. And that's the answer to this. Right? Now, positive over positive. If I didn't have that here, and it just said x approaching 3, and you think about it from the right, because of that square, both sides are positive, right? 3.1 minus 3, it's still going to be positive over positive. It's still going to work like this, right? Now, I just did that if it was just without the direction, right? It would still be positive infinity, right? But this is all we needed to consider for this. Now, you decide, do you really need to draw this number line thing out? Some of you will, and I do recommend it. I tend to, myself, just as a visual reminder. Some of you are sharp cookies and you don't need to. You know who you are, and as you get, maybe for the first few, you might want to practice. Some people are better at visualizing. So you decide whether you actually want to actually write out a number line. That's the way I'm explaining. There's other ways too. Okay. Factoring first then. This is what you do if you substitute. You get what we call, and I don't think you've ever, have you ever used the word indeterminate? Indeterminate? No, don't believe so. Indeterminate means 0 out of 0. That's different than 5 out of 0. You could do different things. Now, you've played around with equations like this before, but you never thought of them this way, don't you? So if you always try to substitute first, do a quick substitution. So I think of this, 6. If I put 6 in here, I see the problem on the denominator, 0 minus 0. If you don't get a 0 on the denominator, you're good. Just do the answer, right? Because mathematically, as long as you have anything but 0 on the denominator, just plug it in. But since we have 0 here, I know I gotta look into this further. Okay, 36 minus 42 plus 6. Okay, it's gonna be 0 on the top. 0 out of 0, that tells me I should factor first. That is one thing I can try. If you could see that you could factor this is something to try. So here I go. You write down limit x approaching 6, because we haven't evaluated the limit yet. Then, factor the top, factor the bottom. I'll pause and you guys take a second to factor both. So once you factor top and bottom, denominator, numerator, you notice that there's a factor in common. Yeah. So I'm going to cancel those two factors out. Can you evaluate now? Yes, you can. And guess what? Once you're evaluating, drop the limit notation. Okay? Now, is it 6 minus 1? I know you don't have to show the arithmetic, but I'm just doing it for instructional reasons. 6 plus 6, so we got 5 out of 12. That's your answer. Couple things. What does this mean? This means if you graphed the original function as given here, you would have a hole at 6 comma 5/12 for the y height. Does that make sense? There's a hole there. That's one thing.
That means the equation doesn't work for it, like you plug that
The
in.
equation itself, as given, as defined, is not, the 6 can't be in the domain as given originally. This equation, that once we cancel things out, this part here, x minus 1, x plus 6 over x plus 6, is practically the same thing, except there's no hole. That's continuous there, right? Like at that spot. Does that make sense? Kind of. You'll get used to it. Okay. How about the next one? 0. This is easy. Well, comparatively. You could quickly see it's 0 out of 0, just by if you tried to plug it in. So, I'm going to try factoring, because I could see I could factor the numerator quite easily. And I'm not going to pause here. X minus 5 over x. I think you can see where this one's headed. Now my trouble spot is gone. This is really, and if you graphed, and you could try this, not right now, but if you graphed that, that's a straight line, the straight line x minus 5, with a hole at 0 and negative 5, right? Okay, and you can evaluate this. So I dropped the limit notation, and I just put 0 minus 5, so negative 5. Now, I'm expecting, like I said, that you can do arithmetic. You don't have to show this kind of a step right here.
Isn't it x plus?
So x approaching 0, so I'm putting in 0 for the x value.
Oh, am I missing?
Yeah, it's cool. Now, a couple things about notation errors that I see, and I'll take off, I'll be chintzy, 0.5 or something out of 2, I'll take it off. I hate showing errors, but I don't want to see this. If somebody wrote down for their next step, this is wrong, and I'm going to erase it because it's wrong. But sometimes people go like this, limit x approaching 0 equals. That is not right. Do you follow me? The equal sign in between? Rubbish. It's adulterous. You can't do that, okay? Don't do it. You heard me. Okay. Yep. Terrible. Okay. You guys are young adults.
I know what you mean, but like,
Okay. Licentious and rude. Terrible. Evaluating limits by simplifying first, and then we'll see where we're at. Okay. Evaluating limits by simplifying first. Okay. If you try substituting, you get 0 out of 0, and it doesn't look like you could factor it too easy. Factoring, you'll get a hunch, right? You could, no, I could factor this. Maybe you can't factor this one. So work it out and see what you get. And this 3 plus h, it almost looks familiar to that first example there that we had, eh? H tends to be something that you see quite a bit. So you're going to have stuff that looks something like that. Well, just do it the hard way then. Multiply it out. So in this case, limit h approaching 0. Oh my goodness. Remember, you get 3 terms when you square this. If you get screwed up with these things, write it out just above. 3 plus h, 3 plus h, 9 plus 3h plus another 3h, so 6h. I'm pretending I'm working this out. Scratch, right? Then the minus 4 times 3 minus 4 times h. I just did the algebra on the top. I can group like terms. The only reason why I kept this bracket here is just to show you where it came from. Sort of thing. That's this chunk. And then group like terms, like I said. I haven't evaluated the limit yet, so I will write this down. Group like terms. Hopefully some good things will happen. Okay, I'm looking at the numbers. 9 minus 12 is negative 3 plus 3. It's 0. That's good. The number zeroes out. Then I'm looking at 6h minus 4h, so 2h. There's only one group of h squared, and it's still positive h squared. Still all over h. All over h. Now I can distribute, divide by h, right? Okay. Oh, no, I will. I'm not going to jump. I'm not going to skip steps. So I'm still going to evaluate the limit after I get 2. The h is divided out. H squared divided by h. So h. 2 plus h. Notation thing. Why do I include the brackets there, but I never did before? When you have a big line on a fraction, it's implied that this is one whole thing. So you don't need the bracket there. But you really should have this here. If you don't, it looks like, and I'll wait for those lines to evaporate, it looks like it's just the limit of h approaching 0 for 2 without the brackets, then plus some h. It's not included. So that's why you need the brackets there. Anyways, it's easy to evaluate. 2 plus 0 is 2. Now, I'll tell you what. I'm not going to work this one out right. I just didn't feel like it, but I will. We'll work this one out, and then we got some problems to try or else prepare. Okay? So, Lord love a duck. Let's take a look here. First thing I do is always double check. 0 on the bottom, okay? And if I do this, I get 3 out of 1, okay? 15 divided by 5 is 3, so 3 minus, okay, I got 0 out of 0. I got to do something else. If it worked there, that I get a number, I would have worked it. Okay. I hate a fraction inside a fraction. What I mean by that is, this is the big fraction, and then I got fractions inside that, right? The little guys. So what I'm going to do, and it's up to you, I'll change colors just so, is I'm going to rewrite this, x approaching 3. You just think this through. Isn't this the same as multiplying this by 1 over x minus 3? This is going to evaporate, but you guys follow? I like just keeping it to 2 lines. That's me. If you want to write big fraction, x over 3, go ahead. Don't be cheap, though, and try to save too many trees. We can recycle the paper. Use the space. Don't crunch it up into a tiny little thing that I can't read. So 1 over x minus 3. Then the top. In order to combine 2 fractions, you need common denominator. So we gotta multiply the first one by x plus 2 over x plus 2. If you could do that in your head, x plus 2 times x, okay, x squared plus 2x. The bottom, I'm not going to multiply out, because I probably don't need to. Don't do any work unless you have to do it. So I'm going to just say the bottom is x plus 2, x minus 2. Now this one's easy to multiply out, but I mean, subtracting 15 times x minus 2. So 15x minus 30. All over the same denominator. We designed it that way. You guys good with this? Now, does this solve our problem yet? Not quite. We still got 0 here, and you'll see, well, maybe. Let's group some like terms on the top, see what happens. So, on the numerator, x squared, nothing else matches with x squared. 2x minus 15x, so minus 13x. Plus, because it's minus negative 30, right? 30. Okay. Can that be factored? Multiplies to positive 30, has a difference of 13, negative side of it. It's 10 and 3. All right, I said has a difference. I was meaning negative. Anyways, adds up to negative 13. Sorry, I said it wrong. It's double negative. That's positive 30. Now, I didn't need the big brackets around here, but I did it just to chunk my work off. Because it's all brackets. But anyways. We get rid of our 0 out of 0 here, though, don't we? Because it was the x minus 3 that was giving us grief. Alan, how are you doing? You got this? Okay. So then, we're good. It's gold now. We know we're not going to get 0 out of this. The reason why you kept this x minus 2, x plus 2 factored for 2 reasons, I'd say. I'd say it's easier to calculate, less chance of mistake when you plug in the 3 if it's just 2 small numbers rather than x squared and so on. Sometimes, even when you factor this, sometimes if this was x minus 2 here, then I would have canceled these out and you have even less to calculate. Sometimes that happens as well. So anyways, I'm going to drop the limit notation and say, well, I'm plugging in my 3. 3 minus 10 is negative 7. 3 minus 2 is 1. Okay, 1 times what? 3 plus 2, 5. Okay. Now, try these assignment questions. I'll just take a look here. And as I mentioned here, by this point, 3 parts in, properties of limits should be intuitively understood, but we're going to look at the properties on page 61 and 2 and ask if you have any questions, but maybe we'll save that till after the test. More about that later. Test.